Hello everyone. I welcome all of you to our module Animal Science and Technology. Today we will be looking into the session 2, Cow Health and the Data Collection. So at the end of this session, you will understand how the callers record and interpret the movement, the rumination and the temperature. We are going to build a simple data logger circuit which is going to count the motion events. In this way, we will be able to view and interpret the simulated sensor data using the Arduino serial monitor. We are going to use the same components just like how we used in the session 1, but we are going to change the coding part and introduce the sensor-based data logging here. Because in the traditional observation, manually we will be noting the cow behavior or the feed intake and then estimating the milk yield from the observation. In the sensor-based data logging, the callers, it's going to record the 24-hour activity, rumination, and temperature. And with that, the data analytics predict the illness earlier. So the algorithms behind it, it can correlate the motion rumination, thereby telling us the milk production and the welfare. So this really matters because the healthy cows have the regular motion or the chewing rhythms, and any sudden drop in these readings, it often indicates a fever or any kind of illness. So this early deduction will save the labor, milk, and cost. That's the reason why we are trying to do these kind of collars. We are going to replicate the components what we used in the previous session, but with a different logic behind it. Okay. So we are going to again utilize the Tinkercad platform. So I request all of you to please go to the Tinkercad platform, give login, personal accounts, and try to sign in with Google. Then click Create and Circuits. We are going to just replicate what we have did in the session 1 DS. So just like session 1, we are going to bring about an Arduino Uno here, followed by a tilt sensor, a LED, and a resistor. So we will be having only one LED now because that's just like a visual activity indicator. So let's try to bring all these components onto the screen. So the first one is the Arduino, followed by an LED, a breadboard small, a resistor, which is being connected to the anode. 330 ohm resistance value is sufficient here. And then a tilt sensor. So just like our previous experiment, we are going to ground all these. So the ground of the Arduino is connected to the negative trait of the breadboard. I'm giving a black wire here. The negative traits are connected together so that the terminal of the tilt sensor can be connected to the negative trait. And terminal 1, we are going to connect to the 12th pin. Again, you can connect to any of the pins. So LED has anode and a cathode. Anode, we are going to connect to the second pin. And cathode, we are going to ground it. So with this, the connections are done. Now it's time for us to move to the coding part. I'll be sharing the coding at the description, and you can paste the code here. I'll be explaining the logic to you dears line by line. So just go to the code and click text followed by continue. Delete the previously existing code and paste the code which I have given in the description below this video. You can also find in the description or you can find it in the comments. The first comment, I have pinned it. Okay. So what we are doing here is we are going to count the tilt events and log the steps into the serial monitor. The code might look like it's having 30 lines, but it is very simple, dears. Let's try to understand the logic first. Okay. So first we are going to initialize the variables. In tilt pin equal to 12, this means that you are going to have a tilt sensor signal pin, which is connected to the 12. Then we have an indicator here. This is just an optional LED indicator. We are connecting to the second pin. Then in tilt val, so this is a variable for the current tilt state. So a tilt state means you can have either the sensor moving or it's not moving, right? So the signal can either be high or low. So we are going to store all these in a variable. So tilt val is a variable for the current tilt state. Then int previous val equal to 1. So this is an interesting component which we haven't used in our session 1. So previous val, just like the name you can see, it is going to store the previous state. Okay. And here it is set to high by default. When I say high, the value is set to 1. So by default, we are going to have this value as high. In step count is equal to 0. So we are going to count the motion events here and we are going to initialize the value from 0. Next, we have the void setup. In void setup, we will be using an internal pull-up resistor. That's the meaning of the 8th line. Pin mode tilt pin comma input pull-up. Followed by pin mode LED pin comma output. So here the LED is being initialized to as an output pin. Then we have the serial begin 9600, which is going to begin the serial communication. And serial println are just how you want to visualize in the serial monitor. These are just print statements. So count activity data logger started. So that's a statement which I want to see in the serial monitor, followed by some hyphens. And all these are just visualizing in the serial monitor. It has nothing to do with the logic, but that's just for the visualization. Then we have the void loop. So in the void loop, tilt val is equal to digital read tilt pin. So we know that we are going to read the sensor state. So read the sensor state and then store it inside the tilt val. Okay. Next comes a very interesting logic. If tilt val is not equal to previous val. So what this means is we are going to see if there is any change or not. So I'm going to look for any changes. For example, whether the value is from low to high or high to low. So I want to deduct a change. And if the tilt value is low, it means that there is a movement deducted. So once the movement is being deducted, I'm going to increase the step count. So step count plus plus is nothing but it helps in increasing my step count value. So in the 5th line, you can see that the step count value is 0. And now we are going to increase the steps. So step count plus plus means we are going to increment the step count followed by an LED to just set it high, and then it's going to print the step is deducted and total number of steps. So this 21 and 22 lines are just a visualization to make us understand that the increment has really happened. So the LED will glow and then in the output, it will be printing like step is deducted and total steps. So serial print statements are generally being used just for our understanding whether the previous command or the instruction has been executed correctly or not. This is one way of debugging, but still we use the print statements then and there in order to see whether the instructions are being executed in a correct order. Okay. Next, serial.println step count. So whatever step count is being enabled, that we are going to visualize in the output. N represents next line. That's all. Okay, so you can see that there is no ln here and there is something called ln in the 23rd line. This just indicates that we are going to the next line. So serial.println step count indicates that we are going to print the updated count, followed by a delay of 200 milliseconds, and then the LED gets turned off. Okay, so here the logic is we are going to deduct the change first, and if the tilt is low, it means there is a movement event happening. Increment the step count, followed by the LED to get turned on and print the various outputs just for our understanding. So this is a logic behind the void loop. And then you have an additional line, the 29th line, previous val equal to tilt val. So what we are doing here exactly is we are updating the previous state, because every time the value should not be initialized from 0. Okay, so we need to update the previous state in order to ensure that the count is incremented correctly. So that's the reason why we have the statement previous val equal to tilt val. So whatever tilt value you are having, so tilt val here in sense, you're reading the sensor state. So all the sensor state value are being pushed inside the previous value. Okay, so we are going to update the previous state. Right, followed by a delay, and this delay is generally given for a stability because you are updating the previous state and then incrementing the step count. So we always give a delay just for the stability here, and then starting to proceed again inside the void loop. So the void loop is going to run forever till you stop the simulation. So that's the reason why we give a delay like 200 millisecond or 50 millisecond, just like a debounce delay or for stability. With this ideology in the code, let's give start simulation now. So you can see here in the 11th line, we wrote count activity data logger started. Just we want to see that in the serial monitor followed by the hyphen. Okay, so whatever you put inside the serial.print, it's just going to come in the serial monitor. Okay, now let's give the, try to move the values here. So once there is a tilt, what has happened here? You can see step deducted, total step 1. Okay, next, again, I'm trying to move. So again, the next step is deducted, total step 2. Next step, total step 3. Then you can see again the step deducted, total step 4. So what we are doing here is we are reading the tilt sensor signal, then deduct any changes in the state, add 1 to the total count, display the count. So this is what we are doing here. In real world, you can compare this like we are capturing the real-time movement data and deducting any posture change or any kind of new movements, which is equivalent to recording the step. Then we are going to send the data to the farm dashboard. So the reason why we give this delay of 200 milliseconds is to avoid the debounce delay. It means it prevents the double counting in a single motion. So a motion is only once, but you should not count it twice. Okay, that's the reason why you give a debounce delay of 200 milliseconds in the code. In this way, we have learned how to build a mini data logger, turning all the motion signals into a numeric data. The counter and the serial monitor is going to mimic how the callers collect or store the movement data over here. I hope all of you understood this activity today. See you all in the next session. Until then, happy learning.